So continuing with trying to understand the wind, we've already talked about how air moves from areas of high pressure to low pressure. When the pressure is relatively the same in a large region, then those are areas that are calm. So now let's take a look at this model of the world, this globe. And of course, the world has two motions. It orbits around the sun. We call that revolution. And then it's also spinning on its imaginary axis. We call that rotation. And that affects the direction of the wind. But even if the world didn't spin or rotate, it would still be windy because there would still be differences in pressure. And that's caused by differences in temperature and humidity and differences in the surface, but mostly by differences in temperature. The reason we have different temperatures is the shape of the Earth. The Earth is a sphere. It's an almost perfect sphere, but not perfect. It's an oblate spheroid, meaning it kind of bulges at the equator, and that's because the world rotates once a day. But every different latitude goes at different speed because the whole thing goes around once every 24 hours approximately. So if you're at the equator, you've got to make the whole way around in one day. You go over 1,000 miles per hour. But if you're at the North or South Pole, you don't go anywhere. Watch this pole as it spins. It didn't go anywhere. So if I could go stand right at, let's say, the South Pole, this is what would happen in 24 hours. That would take 6 hours, 12, 18, 24. I did make a turn, but I didn't go anywhere. My speed was 0. So we live here, so we're certainly going faster than the pole, which is staying still relative to the rest of the Earth, but we're not going as fast as the equator. So these differences in speed are going to cause the wind to appear to curve, and we call that the Coriolis effect. So to demonstrate that, first of all, because of the shape of the Earth, where the sun's rays hit most directly, which is perpendicular or 90-degree angle, is somewhere in the tropics. And the tropics are defined as 23.5 degrees north, that's the Tropic of Cancer, and 23.5 degrees south, that's the Tropic of Capricorn. On any day, somewhere within the tropics, the sun will hit at a 90-degree angle. Of course, where we live is north of that. So if we look out that window, we'll never ever see the sun. We'll see some light that's coming from the rest of the atmosphere, but because we are north of the tropics, we always have to look to the south somewhat to see the sun. So that's where it's going to be the warmest. When you're close to 90 degrees, that's when most energy will be absorbed. As you move farther away from the tropics, the angle gets lower and lower. And every spot on the Earth gets the same amount of light in 1 year, but they get it at varying times. In the tropics, it's close to 12 hours of light and dark every day. If you get to the poles, it's 6 months of light followed by 6 months of darkness. And you might think, well, with 6 months of light, it's going to warm up a lot. But it doesn't warm up very much because the angle is so low that most of the energy reflects. And the surface makes a difference too. Look at Antarctica. It's covered mostly by ice and snow, which is white, and the color white reflects more energy than any other color. So those differences in temperature will cause differences in pressure. Cold air is more dense than warm. So the cold air is going to sink at the poles, and I'm going to show that by drawing H's for high pressure, because cold air is sinking, pushing down high pressure. At the equatorial region, it's relatively warmer, and the cold air sinking forces the warm air to rise, and rising gives us low pressure, so I put a big L at the equator. So even if the world didn't spin, the wind would still blow from the North Pole towards the equator, because wind always goes from high to low. That's in the northern hemisphere. It would also happen in the southern hemisphere, going from the South Pole up towards the equator. So we would still have wind, of course, but we do have the rotation of the Earth. So now I'm going to put it in motion, but I'm going to draw the same line. So it's a little bit tricky, but with my left hand I'm going to turn it while my right hand goes straight. So watch what happens. Okay? And you can see it curved. But did it really curve? Okay? My hand did not go like this. My hand went straight towards the equator, just like it did the first time. The only difference was I was spinning the Earth, so it appears to have made this curve. And that's what we call the Coriolis effect. It's an apparent deflection. It doesn't really happen, but it seems like it happens to us. If we look on the board here, it's named after Gaspar Gustave de Coriolis, and other people had noticed it, but he mathematically showed how to work it out. And it's an apparent deflection, or it can also be called a psychophysical perception. It's what we perceive to be happening, even though it doesn't really happen that way. It all depends on our point of reference. So if we go back to this, objects moving over long distances, such as global wind belts, will appear to curve, and in the northern hemisphere, they appear to curve to the right. And you might look at that and go, but that arrow points to the left. I don't mean you as an observer. I mean, if I'm the wind, or if I'm driving a car this direction, that's a right-hand turn. Now, what's interesting is I spun it this way on purpose because the world rotates from west to east. So I'm going to do the same thing again, same direction, but this time I'm going to go from the south pole towards the equator. So, and my hand will come straight up. So here we go. And you can see in the southern hemisphere, it turns to the left. If you're driving, that's a left-hand turn. So global wind belts turn to the right in the northern hemisphere and to the left in the southern hemisphere. And a similar thing happens with ocean currents. And this leads to a misconception. People have heard that water will go down the drain in one direction in northern hemisphere and an opposite direction in the southern hemisphere. Nope, it doesn't happen over such a small area. It happens over global distances. So that's the Coriolis effect.